1,470 light-years away, something impossible is happening. A star is flickering. Not the gentle, predictable dimming you'd expect when a planet passes in front of its parent sun, blocking a tiny fraction of light, maybe 1% at most. This star is going dark, 22% dark. Imagine every light in your city suddenly cutting to a quarter of its brightness, then surging back to full power days later with no warning, no pattern, no explanation. Now imagine that city is a ball of fusion plasma 900 trillion miles across, and something out there is large enough to swallow nearly a quarter of its light. Something is eclipsing a star with a mass incomprehensibly greater than our entire Earth. And we have no idea what it is. And here's what keeps astronomers awake at night. Here's what makes their hands shake when they pull up the data on their screens. The dimming follows patterns. Mathematical patterns. Rhythms that repeat with a precision that feels deliberate, calculated. As if somewhere out in the constellation, Cygnus, something is counting. Something is measuring. Something is sending a signal we're only beginning to understand. This is the story of KIC 8462852, and what happened when we pointed our most sophisticated instruments at a star that should not exist. The Kepler Space Telescope had one job, and it performed that job with mechanical perfection for nearly a decade. Launched in 2009, this cylindrical spacecraft the size of a small truck floated in the darkness between Earth and the outer solar system, its mirror staring unblinking at a single patch of sky in the constellation Cygnus. 150,000 stars lay in its field of vision, and every 30 minutes, without fail, Kepler measured the brightness of each one. The mission was simple: find planets. When a planet crosses in front of its star from our perspective, it blocks a minuscule amount of light, creating what astronomers call a transit. Jupiter blocking the sun would dim our star by 1%. Earth would dim it by less than 1/100%. These are the whispers Kepler was built to hear, the gentle fluctuations in starlight that would reveal worlds circling distant suns. For years, the telescope did exactly that, discovering thousands of planets, rewriting our understanding of how common worlds are in the universe. But in 2011, something appeared in the data that wasn't supposed to be there. In September of that year, as Kepler's cameras captured the 788th day of observation, star number 8462852 in the Kepler input catalog went dark. Not the predictable tiny dip of a planet. This star lost 15% of its light over the course of a week, as if something enormous had slowly drifted across its face. Then, just as mysteriously, it brightened again. The automated algorithms scanning through the data flagged it as an anomaly. But Kepler was looking at thousands of anomalies every day. Glitches in the detector, cosmic rays striking the sensor, random electronic noise. This particular anomaly was filed away in the vast digital archives, a curiosity among millions of data points, waiting for someone to notice. That someone would be a group of ordinary people who had never set foot in an observatory. They called themselves the Planet Hunters. Scattered across the globe, connected only by the internet, these volunteers represented something new in astronomy. Citizen scientists using their own eyes and minds to do what even the most advanced algorithms could not. The project had launched on the Zooniverse platform in late 2010, barely a year after Kepler began its mission. The concept was audacious in its simplicity. NASA released Kepler's data to the public as raw light curves, graphs showing how the brightness of each star changed over time. Users would log in, look at a curve, and answer a simple question. Do you see a transit? The human brain, evolution's masterpiece of pattern recognition, excels at finding unusual things in noisy data. where computer algorithms searched for the expected, for the regular dips of orbiting planets, human volunteers could spot the weird, the unexpected, the things that made them stop and think, what is that? By 2011, over 300,000 volunteers had joined the search, analyzing millions of stellar light curves. They found planets the algorithms missed. They discovered stellar systems unlike anything in the textbooks. And in the summer of 2013, scrolling through data from a star designated KIEC 8462852, they found something that would change everything. Multiple volunteers kept flagging the same star. The dips in brightness were strange, irregular, nothing like a planet. Some dips were shallow, others deep. Some lasted for hours, others for days. There was no rhythm to it, no periodicity, no pattern that fit any known astronomical phenomenon. The star would sail along at constant brightness for weeks, then suddenly plummet, then recover, then sail along again for months before dimming once more. It looked, one volunteer suggested, like something was breaking apart in front of the star, a swarm of objects of different sizes crossing its face at irregular intervals. The planet hunters flagged it for professional review, and the data eventually landed on the desk of Tabitha Boyajian, a postdoctoral researcher at Yale University. Boyajian sat at her desk in the pale fluorescent light of the Astronomy building, staring at the light curve on her monitor. She had seen thousands of light curves. She knew what planets looked like, what eclipsing binary stars looked like, what instrumental artifacts looked like. This was none of those things. She pulled up all of Kepler's data for KIC 8462852 and spread it across her screen. 4 years of observations, nearly 1,500 days of brightness measurements. For most of that time, the star behaved normally, burning steady at magnitude 11.7, too dim to see with the naked eye, but perfectly ordinary for an F-type main sequence star, about 50% larger and 1,000 degrees hotter than our Sun. Then came the dips. The first major event occurred on day 788. Over the course of several days, the star dimmed by about 15%, recovered slightly, dimmed again, then finally returned to its normal brightness. A week of chaos in an otherwise unremarkable star. The next significant dimming happened around day 1500, and it was worse. The star's light dropped by 22%, the deepest dimming Kepler had ever recorded for a single stable star. To put that in perspective, if you replaced our Sun with KIC 8462852 and watched this dimming event from Earth, the sky would darken as if a massive storm cloud had rolled over the entire planet. Then, around day 1540, another cascade of dips, a complex series of brightenings and dimmings that looked like something fragmenting, tumbling, breaking apart. Boyajian ran through every explanation she could think of. A planet? No planet could block that much light. Jupiter is enormous by planetary standards, 1/10 the diameter of the Sun, and even Jupiter transiting a solar-type star would only cause a 1% dip. To block 22% of the light from KIC 8462852 would require something half the size of the star itself. Planets don't get that big. Binary stars do. But KIC 8462852 showed none of the regular periodic dimming you'd expect from a companion star. An eclipsing object would dim the star on a predictable schedule, every orbit like clockwork. This was anything but clockwork. This was chaos. News of the discovery rippled through the astronomical community like a shockwave. By September 2015, Boyajian and her colleagues had published their findings in the monthly notices of the Royal Astronomical Society, carefully titled Planet Hunters 9, KIC 8462852, Where's the flux? The paper was a model of scientific restraint, methodically ruling out explanations one by one, acknowledging that the phenomenon defied easy categorization. But within days of publication, the story exploded into the public consciousness, and the reason was a single word that appeared in early discussions among researchers: artificial. The speculation began with Jason Wright, an astronomer at Penn State University, who suggested that if no natural explanation fit the data, perhaps the answer was technological. An advanced civilization might build enormous structures around their star to harvest energy, structures large enough to block significant amounts of starlight. Freeman Dyson had proposed the concept decades earlier: a swarm of solar collectors encircling a star, capturing its energy for a civilization's use. If you were an astronomer in a distant galaxy looking at our sun and humanity had built such a megastructure, you would see exactly what Kepler saw at KIC 8462852. Irregular, non-periodic dimming as the swarm of structures moved in their orbits, blocking light in unpredictable patterns. The media seized on the idea with ferocious enthusiasm. Headlines screamed about alien megastructures. Social media erupted with speculation. Suddenly, KIC 8462852 had a nickname that would stick: Tabby's Star, after the astronomer who had brought it to the world's attention. And in the background, lost beneath the noise of excitement and speculation, was a quieter, more unsettling discovery: the patterns. The star wasn't just dimming. It was dimming in ways that suggested something beyond random chance. Deep in the data, researchers began finding things that made the hairs on the back of their necks stand up. Fourier analysis, a mathematical technique for detecting hidden periodicities in complex data, revealed that embedded within the star's chaotic flickering were regular rhythms: a signal at 0.88 days, another at approximately 11 days. The numbers themselves weren't extraordinary, but their precision was. Natural phenomena are messy. Comets tumble, dust clouds swirl, planetary debris spirals in chaotic orbits governed by the gravitational tug-of-war between multiple bodies. Yet here, in the noise of Tabby's star's light curve, were frequencies that repeated with a regularity that seemed too clean, too organized. Researchers Andrew Collins and Rodney Hale took the analysis further. They noted that the 11-day cycle aligned with multiples of 11, a prime number. Prime numbers don't occur often in nature's random processes. They're the building blocks of mathematics, the atoms of number theory, and they have one particular significance: they're universally recognizable. Any intelligence capable of mathematics, regardless of where in the universe it evolved, would recognize prime numbers. The physicist Luke Arnold had suggested in 2005 that if an advanced civilization wanted to signal its presence, one way would be to create deliberate patterns in the light from their star. Build structures that transit the star in sequences based on prime numbers. Encode mathematical information in the timing of the dips. Make it obvious that the signal was artificial, because nature doesn't count in primes. The periodicities in Tabby's star's light curve seemed to be doing exactly that. The 24.2-day cycle, the harmonics clustering around 0.88 days. The way these rhythms interlocked like gears in an impossibly vast machine. It all felt too precise, too structured. Some researchers went further. They noted that the 11-day cycle synchronized with Earth's own solar cycle in meaningful ways, as if the pattern were calibrated to be noticeable specifically to observers on our world. As if something 1,400 light-years away was sending a message meant for us. The scientific community pushed back hard against these interpretations. Correlation isn't causation. The human brain is exquisitely good at finding patterns, even in random data. But the numbers were there, documented in peer-reviewed papers, reproducible by anyone with access to the data. Whether they meant anything, or were merely an artifact of our pattern-seeking minds, remained frustratingly an open question. The attention Tabby's star received did something unprecedented in modern astronomy. It turned citizen funding into a research tool. In the spring of 2016, Tabitha Boyajian launched a Kickstarter campaign with a straightforward pitch. Give us money, and we'll watch this star continuously. Kepler had observed the star for 4 years, but it had moved on to other parts of the sky. If Tabby's star dimmed again, Kepler wouldn't see it. But ground-based telescopes could. The Las Cumbres Observatory Global Telescope Network operated a fleet of robotic telescopes scattered across the world, always pointed at the night sky somewhere. For $100,000, they could devote continuous monitoring to a single star, catching dimming events in real time, analyzing the light with spectrographs to determine if whatever was blocking the star was solid or gaseous, opaque or translucent. The campaign raised its goal in days. More than 1,700 people contributed over $100,000, enough for a full year of observations. It was, in a very real sense, the public directly funding the search for something that might be extraterrestrial. The telescopes began their vigil. Months passed. The star burned steadily. Then, on May 18, 2017, it began to dim. Alerts went out to astronomers worldwide. Social media lit up. This was it. The first dimming event captured in real time since the original Kepler observations. Over the following weeks, the Las Cumbres telescopes tracked the star through 4 distinct dipping events, measuring not just the overall brightness, but the color of the light being blocked. What they found was both disappointing and deepening the mystery. The dimming affected different wavelengths of light differently. Blue light was blocked more than red light. Exactly the signature you'd expect from dust, not a solid object. An alien megastructure, something with hard edges and opaque surfaces, would block all colors of light equally. Dust doesn't. The tiny particles scatter blue light more efficiently than red light, which is why our sky is blue and sunsets are red. The new data seemed to rule out the megastructure hypothesis. But it raised a more disturbing question. If dust was causing the dimming, where was it coming from? And why was there so much of it? The problem with the dust explanation was scale. To block 22% of a star's light requires an absolutely staggering amount of dust. Imagine pulverizing the entire Earth into microscopic particles and spreading them in a vast cloud around the sun. You'd block maybe a fraction of a percent of the sun's light, and only for a brief time before the dust either fell into the sun or was blown away by solar radiation pressure. Whatever was creating the dust clouds around Tabby's star had to be enormous, recent, and ongoing. Comets became the leading natural explanation. A family of comets, thousands of them perhaps, orbiting the star in a tight swarm, each one shedding dust and gas as they approached their parent sun. If you caught such a swarm in the middle of breaking apart, maybe after a collision with a larger body, you might see irregular dimming as clouds of debris crossed the star's face. But even this explanation stretched the boundaries of plausibility. The deepest dimming suggested dust clouds dense enough to block light across a region larger than the star itself. That would require not just a few comets, but the equivalent of hundreds of millions of comets, all in the process of disintegrating simultaneously. Planetary collisions offered another possibility. If 2 planets had collided in the Tabby star system, the debris would spread into a vast disk of dust and rock, gradually clearing as pieces either fell into the star or were ejected from the system. But planets collide on timescales of millions of years, and the debris would clear on timescales of thousands. The odds of catching such an event in progress, during the 4 years Kepler happened to be watching, were vanishingly small. And then there was the long-term dimming, the discovery that would make everything more complicated, more unsettling, more impossible to explain. In 2016, astronomer Bradley Schaefer published an analysis of archival photographic plates, glass sheets with light-sensitive emulsions that astronomers had used to photograph the sky before digital cameras existed. The Harvard College Observatory's plate collection contained images of Tabby's star going back to 1890, over a century of data. Schaefer carefully measured the star's brightness on plates spanning from 1890 to 1989 and found something extraordinary. The star had dimmed by about 16% over the course of a century. Not irregular dips, a gradual long-term fade, as if something were slowly enveloping the star, cutting off more and more of its light decade by decade. Other researchers scrutinized Kepler's own 4 years of data and confirmed a similar trend. During just those 4 years, Tabby's star had faded by about 3%. If this long-term dimming continued at the same rate, the star would be half as bright in a century. In 2 centuries, it might be dark. The scientific debates intensified, fracturing into competing camps, each with their own interpretation of the accumulating data. Natural explanations proliferated, each more baroque than the last. Perhaps Tabby's star had recently captured a rogue planet, and the tidal forces were tearing it apart, creating clouds of debris. Perhaps the star harbored an unusually dense disk of material left over from planet formation, material that should have cleared away billions of years ago, but somehow persisted. Perhaps we were watching the aftermath of a collision between 2 Kuiper belt-like objects, massive icy bodies from the outer reaches of the system smashing together and filling the inner system with dust. Each explanation worked for some aspects of the data, but failed for others. The comet swarm couldn't explain the long-term dimming. The planetary collision couldn't explain why Kepler saw multiple separate dimming events over just 4 years. The captured planet scenario was statistically so improbable that invoking it felt like admitting defeat. And hovering at the edge of every discussion, never quite dismissed but never quite embraced, was the artificial hypothesis. Some researchers noted that if you were building a Dyson swarm, you wouldn't complete it overnight. You'd construct it piece by piece, structure by structure, over decades or centuries. An observer watching such construction would see exactly what we were seeing. Irregular dimmings as new structures were moved into place, and a long-term fade as more and more of the star's light was captured by the growing swarm. The mathematical patterns in the light curve, the prime number periodicities, the way the cycles seemed almost too regular to be natural. All of it could be explained if the dimming were deliberate, controlled, engineered. But this explanation required accepting something profound and unsettling. That we were not alone. That somewhere in the constellation, Cygnus, 1,400 light-years away, an intelligence had arisen, built a civilization, and was now reshaping its entire solar system. That we were watching, in real time, the signature of engineering on a scale so vast, it made all of human technology look like the scratchings of insects. The SETI Institute pointed their radio telescopes at Tabby's star, listening for signals. They heard nothing, only the background hiss of the cosmos. But as some researchers pointed out, the threshold for detection was set extraordinarily high, requiring a signal powerful enough that it would drain the energy output of an entire planet just to generate it. If there was a civilization at Tabby's star, and if they were transmitting, we might not have the ears sensitive enough to hear them. The star continued to behave exactly as mysteriously as it had from the beginning. Throughout 2017, the Las Cumbres Observatory tracked several more dimming events. In late September, a dip of 0.3%. In October, a curious brightening event, where the star temporarily appeared slightly brighter than its baseline, as if something reflective had passed in front of it, bouncing light in our direction. In November, another major dip, this one reaching 1.25% and lasting for weeks. With a complex structure of multiple overlapping dimming events, as if several clouds of material were crossing the star at slightly different times. Each new observation added more data, but the data refused to converge on a single explanation. Instead, the mystery deepened. Researchers discovered that Tabby's star wasn't quite as unique as initially thought. In 2019, astronomer Michael Schmidt identified 21 other stars exhibiting similar behavior: irregular, unpredictable dimming with varying depths and durations. 15 were slow dippers, like Tabby's star, showing gradual dimming events. 6 were rapid dippers, exhibiting even more extreme variability. If this type of behavior was common enough that Kepler found it in multiple stars within just one field of view, then perhaps it wasn't caused by rare, catastrophic events like planetary collisions. Perhaps it was a natural but poorly understood phase in stellar evolution, something that happened to certain types of stars under certain conditions. But what conditions? Another star, designated EPIC 20437607, demonstrated dimming even more extreme than Tabby's star, dropping to 80% of its normal brightness in a single dramatic event. The light curve of that event showed the signature of something with a ring system, like Saturn scaled up to monstrous proportions, crossing in front of its star. If ringed objects could cause dimming that extreme, maybe swarms of smaller ringed objects could explain Tabby's star. Maybe. Probably. The qualifiers piled up like a cairn of stones marking uncertainty. Each potential explanation was followed by a caveat, a problem, a piece of data that didn't quite fit. The star remained, as it had from the beginning, an anomaly that resisted every attempt to force it into the comfortable categories of known astrophysics. By 2024, nearly a decade after the initial discovery, the enigma of Tabby's star had evolved into something more subtle but no less profound. The latest observations suggested that the irregular dimming events were indeed likely caused by dust of the right size and composition to explain the wavelength-dependent dimming. The long-term fading that had seemed so dramatic in the archival data had become more controversial, with some researchers questioning the calibration of century-old photographic plates. The alien megastructure hypothesis, while never definitively disproven, had faded from serious scientific discussion, relegated to the realm of interesting speculation rather than active research. Yet the star refused to be fully explained. The sheer amount of dust required to cause the observed dimming remained difficult to reconcile with any known astrophysical process. The mathematical patterns in the dimming events, whether real signal or pareidolia, continued to haunt the data. Patterns that looked like they might mean something, if only we could figure out the code. And there was something deeper, something philosophical about Tabby's star, that transcended the specific question of what was causing its light to dim. For the first time in human history, we had found something in the cosmos that we couldn't immediately explain, something that forced serious scientists to consider, even briefly, that we might be looking at the work of another intelligence. Even if the final answer proved to be natural, even if every anomaly eventually found its place in the framework of known physics, that moment of uncertainty was itself revolutionary. For a few years between 2015 and 2018, We lived in a universe where the possibility was real and present, where every new data point might be the confirmation we were seeking, where the dimming of a distant star carried the weight of cosmic significance. The star kept dimming and brightening according to its own inscrutable schedule. Scientists kept watching, kept analyzing, kept publishing papers proposing new models and ruling out old ones. The data accumulated in vast databases, each light curve measurement adding one more pixel to the picture of a star that remained stubbornly unwilling to conform to our expectations. Some researchers joked that KIC 8462852 should be renamed Tabby Star permanently, not just as an informal nickname, but as an official designation, in honor of the astronomer who had recognized its significance and in recognition that it had become, in a very real sense, her life's work. Others suggested calling it the WTF star, short for Where's the Flux, the title of the original discovery paper, though that acronym carried obvious alternative interpretations that the astronomical community found both amusing and appropriate. What haunted researchers most wasn't the dimming itself, but the timing. The Kepler telescope operated for 9 years. During that brief window, purely by chance, it happened to be pointed at a star undergoing whatever process was causing these dramatic, irregular dimming events. If Kepler had launched 5 years earlier or 5 years later, it might have seen a perfectly normal star. The events could have started in 2010 and ended in 2014, a blip in cosmic time, over and done before we ever thought to look. The odds of catching such a transient phenomenon, if it was indeed transient, were extraordinarily small, unless it wasn't transient. Unless whatever was happening to Tabby's star had been happening for centuries, for millennia, was still happening now, would continue happening for centuries more. The long-term dimming trend, if real, suggested something ongoing, something persistent, a process that unfolded across human timescales rather than astronomical ones. A civilization building a Dyson swarm would take centuries to complete the project. A civilization in the process of dismantling their planetary system to build such structures might work on timescales of thousands of years. From their perspective, if they existed, we would be momentary observers, blinking into awareness for an instant, noticing their work, then blinking out again as our own civilization either advanced to the stars or destroyed itself, all within a time frame that for them might be the equivalent of a single afternoon. The thought inspired both awe and melancholy. If we were seeing the signature of another intelligence, we were seeing it across a gulf of 1,400 years. The light reaching our telescopes left Tabby's star around 625 AD. When the Maya civilization was at its height, when the Sui dynasty unified China, when Muhammad had not yet been born. Whatever was happening there, if anyone was there to do it, they were seeing light from Earth that left when the Roman Empire still existed. They were looking at a planet that would not develop radio technology for another 1,300 years. If they sent a message tomorrow, we would receive it in the year 3425 AD. If we replied, they would hear us in 4825 AD. The gulf was so vast that conversation was meaningless. We could only watch, frozen in time, observing the past as if it were the present, forever unable to interact, forever separated by the impassable barrier of the speed of light. There is a telescope, even now, still watching Tabby's star. Ground-based observatories continue their vigil, automated systems capturing the star's light every clear night, building up a data set that spans years, looking for patterns, for changes, for any clue that might unlock the mystery. The citizen scientists who first noticed the anomaly, scattered around the world, still log into their computers, still scan through light curves, still search for the next tabby star, the next impossible thing hiding in plain sight in the data. The data itself. Petabytes of information gathered by Kepler over its 9-year mission, sits in archives, accessible to anyone with an internet connection. Thousands of stars observed, millions of data points recorded, and within that vast data set, almost certainly, are more mysteries waiting to be found. More stars that don't behave the way they should. More anomalies that will force us to expand our understanding of the universe. More moments of profound uncertainty where we must confront the limits of our knowledge and the possibility that some things in the cosmos might not be natural at all. Tabitha Boyajian, the astronomer for whom the star is named, continues to study KIC 8462852, publishing papers, analyzing new data, carefully avoiding the hype while remaining rigorously committed to understanding what's actually happening 1,400 light-years away. She has become, almost despite herself, the face of a mystery that captivated the world. The scientist who discovered something that might be nothing, or might be everything. When asked in interviews what she thinks is causing the dimming, she is careful, measured, scientific in her response. Probably dust. Probably some natural astrophysical process we don't fully understand yet. Probably something that will eventually make sense when we have enough data. But there is always a pause after such statements. A brief moment where the possibility hangs in the air, unspoken but present. The possibility that she discovered something that would change everything. The possibility that somewhere in the constellation Cygnus, around an otherwise unremarkable F-type star, something is counting in prime numbers, something is building, something is waiting to be understood. The constellation Cygnus is visible in the northern hemisphere from summer through fall. A cross-shaped pattern of bright stars representing the swan flying south along the Milky Way. Deneb marks the tail of the swan, one of the brightest stars in the night sky. Halfway between Deneb and Delta Cygni, in a region dense with faint stars, is KIC 8462852. You can't see it without a telescope. Even with a decent amateur telescope under dark skies, it appears as nothing more than a dim point of light, indistinguishable from thousands of other stars in the same field of view. There is no way, looking at it, to know it's special. No way to know that its light has been dimming and brightening in patterns we still don't understand. No way to know that embedded in that faint flicker might be a message, a signal, a deliberate pattern counting out prime numbers in the universal language of mathematics. But it's there. It has always been there, dimming and brightening across the centuries, across the millennia, its light traveling through the vast emptiness of space, crossing the distance between stars at the speed of causality itself, arriving at our telescopes carrying information encoded in brightness fluctuations, in wavelength shifts, in patterns too subtle for our eyes but perfectly visible to our instruments. We are, perhaps for the first time in human history, sophisticated enough to notice. We have built telescopes sensitive enough to measure the brightness of stars to a fraction of a percent. We have launched those telescopes into space, away from the obscuring atmosphere, where they can stare at the same patch of sky for years without blinking. We have created massive databases to store the resulting data and built communities of citizen scientists to analyze it. We have developed the mathematics to find patterns hidden in noise, the physics to model stellar phenomena, the spectroscopy to determine the composition of dust clouds 1,400 light-years away. We are living through the first moment in 4 billion years of life on Earth, when a species has developed the capability to detect the signature of another technological civilization, if such a signature exists. Whether we have actually detected such a signature at Tabby's star remains an open question. But the fact that we can ask the question, that we have the tools to investigate it, that we are actively searching the cosmos for signs of intelligence beyond our own, represents something profoundly new in the history of the universe. Somewhere, out beyond the orbit of Neptune, well beyond the reach of sunlight warm enough to melt ice, the Kepler Space Telescope drifts in the darkness. Its fuel tanks are empty. Its reaction wheels are frozen. Its solar panels no longer generate enough power to run its instruments. But the data it gathered over 9 years of operation will outlive all of us. Stored in archives, analyzed and reanalyzed by generations of astronomers, yielding discoveries that its designers never imagined. That spacecraft, dead now but still drifting in the void, still trailing Earth in its orbit around the Sun, is the reason we know about Tabby's star. The reason we can ask whether we are alone in the universe. The reason we have evidence, however ambiguous, however frustratingly incomplete, that something 1,400 light-years away is doing something we cannot explain. And 1,400 light-years away, the star keeps burning. Hydrogen fuses to helium in its core, releasing the energy that makes it shine. Energy that pours outward through the star's layers, erupting from its photosphere as light and heat, streaming into space in all directions. Most of that light travels forever into the empty darkness between stars, going nowhere, seen by nothing. But some of it, a tiny fraction, is blocked by something in orbit around the star. Something that causes irregular dimmings. Something that may or may not be natural. Something that may or may not be counting in prime numbers. Something that may or may not be trying to tell us that we are not alone. The light that gets past, the light that isn't blocked, travels outward at the speed of light. 8 years from now, that light will pass Mars. 14 years from now, it will reach Earth, strike our telescopes, be measured, analyzed, added to the ever-growing data set. And astronomers will look at those measurements, searching for patterns, searching for answers, searching for some clue that will finally explain what's happening at KIC 8462852. Searching, perhaps, for a message in the flickering light. Searching for evidence that something out there, somewhere in the vast cosmos, is looking back at us with equal wonder, equal curiosity, equal loneliness in the darkness. Searching, ultimately, for proof that we are not the only ones who look up at the stars and ask, is anyone there? The star dims. The star brightens. The pattern continues. Whether we watch or not, whether we understand or not. Counting out its cryptic rhythm in the darkness, a lighthouse in the void, transmitting a message we may never fully decode. And we keep watching. Because that's what we do. Because we are a species that needs to know. Because somewhere in that flickering light might be the answer to the oldest question we have ever asked. What else is out there beyond our small blue world? What else waits in the darkness between the stars? What else lies hidden in plain sight, encoded in starlight, waiting for us to be clever enough, patient enough, persistent enough to finally understand? The constellation, Cygnus, wheels across the autumn sky. The stars burn, the universe expands, and in one small corner of the cosmos, on a planet circling an unremarkable yellow star, a species that learned to think, learned to wonder, learned to build telescopes and launch them into space, continues to search for an answer to a question that may have no answer. Or may have an answer so profound that understanding it will change everything we thought we knew about our place in the universe. The light from Tabby's star continues its journey, crossing the void, carrying its mystery, its patterns, its possibilities. We wait, we watch, we wonder. And somewhere, 1400 years in the past and 1400 light years away, something that may be nothing or may be everything, continues whatever it is doing, dimming the light of a distant star in patterns we cannot explain, in rhythms we do not understand, in a cosmic message written in starlight that we have only just begun to read.